Well, good afternoon, everyone. I'm Khaled Musamman, and welcome to another special seminar that's organized by the Pacific Earthquake Engineering Research Center, PEER. And it's really, I know we always say it's my pleasure, but really it's my pleasure to introduce a good friend and a former and current colleague too.
Yeah.
In another places, okay. So, Professor Stojadinović, who have been with us for several years, and currently he's in Zürich, very nice place, ETH. He is the chair of structural dynamics. Let me get this right.
And earthquake engineering.
Structural dynamics and earthquake engineering in ETH, and he has been educated in this place with a Ph.D. a year before me, in '95.
And was in this room in 511 for like forever.
Also, he has a degree from Carnegie Mellon. He has a degree from Belgrade, and he works in several areas. One of them I'm very much familiar with. His work in hybrid simulation. He also works on resilient systems and rocking systems, and hopefully we're going to hear about that. Professor Stojadinović have been here in Berkeley for several years, and in the past 4 years?
Well, I left about 4.5 years ago, but I was here for like 11 as a professor.
The rooms still look the same. So.
Well, that basket is new.
Okay, something new.
Something
so, without further ado, Professor Stojadinović.
So anyway, so what I wanted to do is to tell you about one of the areas that people in my group are working on in Zürich, and that is the topic of resilience of civil infrastructure systems. And this is a topic that somehow has gained some popularity recently, and we'll see how that popularity is going to last. But the idea is to talk about communities, to talk about places that have a geographic boundary and then somehow are working together to keep their social and political and economic life going. The size doesn't really matter. This is us here in Berkeley. That was Zürich, about 8-9 times smaller. But nevertheless, there is a bounded place where the fate is shared under normal life and under natural hazards. And then, especially after Katrina, but not only after Katrina, there were several iterations of the notion of what it takes for a community to survive, in the sense that there are places in Nevada that are ghost towns. These are the towns where this survival of inhabitants didn't happen. People just left. But what we're really interested in is to see what does it mean to not give up? What does it take to not give up? And there is probably a lot of things in psychology and social science and policy that people can talk about, but we are civil engineers. So what I'm going to do, what I think we should do, is to say, fine, the community resilience depends on the resilience of its infrastructure, and then put the ball in our court in some sense. So the idea that I will, the content of this talk will be on the behavior of civil infrastructure systems and their resilience. And this is one of the many diagrams that people have drawn about what's important for the functioning of a community from this engineering standpoint. And obviously public safety is at the cornerstone, and we have been doing public safety as civil engineers for many thousands of years. And lately, since we had developed some design codes, we have a public safety in mind in terms of our codes being calibrated to prevent collapse and not to kill people. But that is one layer that is then surrounded by a few other layers that contain the social and the economic life of a community. And then here is the one that I'm interested in. This is the layer of infrastructure systems that supply the energy, the water, the communication, the transportation, and the waste management for our society. And so this is why we could possibly say that without the functioning of these kinds of systems, resilience of a community cannot be realized. These are quite fundamental to the life of a community. Unfortunately, they are not simple. And this graph is not meant to be understood. It's meant to show the spaghetti that are connected, the different infrastructure systems, and that are representing in some sense the complexity of what we need to deal with. There is basically the idea that the infrastructure systems are going to supply another system that we shouldn't forget about, and that's the system of houses, be it private or public, that are hosting or housing the population. And all the infrastructure systems that we deal with are highly interconnected, and they are going to be more and more interconnected as time goes by. We are going to be facing a situation very soon when we develop these smart systems where, if we're not already doing so, where the control and command of such systems is going to be so dependent on the telecommunications and computer networks that they're going to be indistinguishable and unseparable. And so a failure in one may lead to the failure in the other, and therefore cascades could happen, which then tremendously complicates the engineering of such systems and tremendously increases the risk exposure. And so this is in some sense reality which I think the model that I'm going to talk about doesn't yet approach, but at least the hope is that at some point in time we will be able to deal with a complex system. And the idea that we would like to do to enable design is to somehow quantify resilience. While there is a lot of talking and descriptions of resilience, there has been one paradigm that somehow caught on that describes resilience as a process in time and draws it on a graph where the vertical axis is the functionality of a system or a community, and then there is an idea that there is a drop of that service and then a slow recovery of that service, and the integral above or underneath this curve is the loss of whatever, loss of functionality, and therefore the rest of this white space is the resilience of that system. And this, as far as I know, was first proposed by Michel Bruno and the guys at MCR in 2003 or so. Maybe there was some earlier graphs like that. But when you give an engineer a graphical representation of this type, then immediately there is people who can integrate, and they do this, and they say, oh great, now we can quantify the thing. There is also other imaginative people who start to classify the behavior of the system as in terms of collapsing or ductile or robust, or even better than it used to be, somehow adapted to the new conditions. So there has been a lot of imagination that people can do with this kind of graph, but sadly not too much quantification in terms of how do we parameterize this graph, how do we compute this area. There are very simple models, there are models that are more complicated, that are deterministic, that are probabilistic, but the one that I would like to present is the one that is based on the concept of supply and demand. The reason why I find this very interesting is because the civil infrastructure systems that we deal with are supplying something, and there is a demand from the population, from the houses that are using this quantity. So in terms of electricity, there are the generation stations that are then the power is being generated, transmitted, distributed to a variety of users, consumers. And in that sense, I found it very interesting that not too many people had looked at the problem of resilience of a civil infrastructure system in the supply-demand space, in the supply-demand paradigm. So the way that I propose to do this is that we take the same concept of resilience but separate it into the supply side and the demand side. So again, an infrastructure system that supplies something, electricity for example, will suffer some kind of a fairly fast degradation of this functionality, and then start to recover probably more slowly. This kind of process we can hopefully monitor and simulate. And the same we can do for demand. Now the demand comes basically from the people, from the population. And the thing that what we did is to say that the demand is somehow proportional to the amount of physical damage into the housing inventory. That includes also the hospitals and offices and everything else. But let's say that there are some that we will have an idea of how damaged the houses are, and with that idea we can then somehow speculate how much power they could use or how much time it would take them to be able to consume power in the people to come back to their dwelling and start consuming power, be it just to charge a cell phone, which is very little, or to start using the full facilities of an office, air conditioning, and possibly even a server farm or something like that. So again, there is some kind of a drop which possibly lasts longer, and the recovery which lasts in another recovery process takes another rate and develops in another time from the supply. And overlapping the two, what we can see is that there is a region in time where the supply is not meeting the demand. The drop in the supply is too severe, the drop in demand is not so severe, and in that sense, the lack of resilience of a civil infrastructure system is exactly that. It is this area. Here, it's interesting, but there in this time interval, the system is meeting, the supply system is meeting the demand that the community imposes on it. And true enough, it is only half of what it used to be, but the systems are capable of meeting the demand. The rate of recovery of the demand and the rate of recovery of the supply are therefore crucial for understanding this. So it's not only the absolute values as to how much drop there was, but also there is a velocity factor, there is a rate that is associated with this kind of a system. And so now we can still do the integral. We can still integrate this area and try to devise a system to quantify the lack of resilience that we see here, the situation during time that produces where the system doesn't satisfy the demands from the community. And this is quite interesting for many reasons, and I'll talk more about why I think it has a few advantages, but one of them is that in many cases we have been faced with a question as to how much should we recover? Do we need to adapt? Do we just need to come back to where we were before? What is the right level? And here in this formulation, the right level is only that. You just need to meet the demand, and as things evolve, you keep up. But as soon as you met the demand, you're not deficient in resiliency anymore. Your system is working. And so the question then, if this is the definition, if this is the approach, the question is how do we compute this integral? How do we actually figure out this area, and what do we do to find some numbers? Do we approach the problem at the component level? Do we look at the system level? Do we look at the system of systems level for the entire community? And what is the right way to figure this out? And in this sense, what we did is to go back to the basics, to go back to the peer performance-based design formulation, where the idea is that everything is local. Damage happens locally, and even though this entire substation was shaken, possibly only one insulator fell. And even though this earthquake was a spatial phenomenon, this piece of equipment is damaged very locally. The same goes for switches, the same goes for other elements of the power supply system, and similarly, damage to the housing inventory is also local. And there are numerous examples where we have areas of the city that are shaken with about the same intensity, and different buildings are standing and the other ones are not. And there we can draw again we can rely in some sense on the local damage evaluation, because we have done this. We have done local damage assessments and local performance assessments within the peer framework. And so in that is why we fundamentally rely on the fragility functions or vulnerability functions to assess the damage that has happened to the infrastructure system and the damage that has happened to the housing inventory, and then from there compute the lack of supply or the lack of demand. And these vulnerability functions, fragility functions, are conditional probabilities. They do tell us what is the probability that the damage, the loss of functionality is higher than a threshold given some intensity of the earthquake. So this is straight out of the standard Peer framework and the standard Peer equation formula. And fortunately, over time, this is not something new. I think maybe it all started with the Vision 2000 document, and then certainly went on through the existence of the NSF Peer Center, and then keeps going on through the existence of the Peer Center, the development of new and cataloging of existing fragility functions. And here in the US we do this, the HASUS people do this, and in Europe there is the global earthquake model people in Pavia who do this cataloging. And in general, now these days there is a high probability that pretty much any type of equipment or substation or house anywhere that one can find a competent enough, trustworthy enough fragility function to use to assess damage and vulnerability of the system. However, repair is also very local. We approach repair one by one, house by house, transformer by transformer, wall by wall. And in that sense, we also must go down to the component level and address not the vulnerability part, but also the recovery part. And this is, in some sense, a construction management exercise. One looks at the amount of damage and one can estimate the repair time and repair cost. And again, fortunately, this is also what we did in Peer. And I was fortunate enough to be working on the bridge part there, and some other colleagues were working on the building part. And we did develop repair time and repair cost fragility function, recovery functions in some sense for the California bridges. And so there is some experience, but not nearly as much as there is experience in vulnerability functions. Basically, it's not very, very easy to find recovery functions. There are a few listed in HASUS that have been ported over from ATC 13 or recently a little bit developed forward, but very few of such functions exist. And this is one relatively simple challenge that we can address immediately, in the sense that once we make vulnerability functions and figure out the fragility of a piece of infrastructure, then we should try to assess the repairs. We should try to plot out how much time and what is the cost, what is the people effort, how many crews does one need to affect the repair of a damaged piece of infrastructure. And these recovery functions will or need to, in this framework, look very much like the inverse of the vulnerability function. There are also conditional probabilities, this time conditioned on the level of damage, that give a probability that the functionality will be restored, but there is a time parameter, there is a duration parameter measured from the date, the moment that the event occurred. And so we will have families of recovery functions that are parameterized by the amount of time that passed and the amount of time that was available to affect the repairs. And of course, after a very long time, the hope is that we will have repaired everything. Therefore, the probability of functionality will be very high. But after a few hours or days, the probability of a piece of infrastructure coming back to full function is relatively low. And so the mathematical form of both vulnerability and recovery functions could be a log normal cumulative distribution function. But also at Stanford there was a recent PhD thesis by David Lallemant where he and Anne Karmidjian used Weibull functions. And they have been also fairly successful. And there are some advantages of such functions to be used as these kinds of probability distributions. So, and this is fine, working on the local level is okay, but there is one more thing that we have to take into account. And this thing is the functionality, the operation of the system. We are dealing with the system. Even if it is the system of houses, it is still a somehow interconnected system, but definitely it is so for the infrastructure system. An infrastructure system, and this example is again the electrical power system has several components: generation, transmission, transformation, distribution, and in the end consumption, that follow certain physics. One must balance power in the system. There is the voltage balance must exist. One cannot let infinitely large currents run through it. Everything will burn. One has to look at the availability of particular sources and the availability of particular consumers during the dispatch operation. And the companies that do this for money, they definitely do it with respect to some kind of cost. And there is a concept of economic dispatch that people have developed, especially now when they have different sources of green power, less green power, and very dirty power, and different pricing systems. And so the normal dispatch is something that on which the IEEE people and the electric power people have books and the journals, and this is a known problem. A somewhat less known problem, but not that different, is the emergency dispatch, the one that happens when there is damage. In those situations, the electric power company faces a dilemma. Should they be making money, or should they be supplying power where it's most needed for recovery? And sometimes they choose to supply the Google disk drive plant because this is a sure paying customer instead of the hospital. And this is something where we could possibly intervene in terms of choosing the strategy for emergency dispatch. But again, the problem is the same. If there is damage in the network, how do you distribute power? What parts of the network are not going to be accessible? Where are the islands, in some sense, where the power is plentiful but the consumers are damaged, or otherwise where there is a lot of workable homes, but there is just simply no transmission, no power, no substation working there, and they cannot be supplied. And so with this kind of a model, with this model that has the vulnerability functions and the recovery functions at the level of individual components, and the model of the operation of the system, we were able to do simulations 1, 2, 3 n days after the event and compute the generation capacity, the available power, and the power demand in a hypothetical region. This is the IEEE 118 network, a piece of that. We assume that it is being hit by an earthquake, that there is some kind of distribution of intensities, that some of these nodes represent generation facilities, some represent distribution facilities, some of these nodes are cities where the demand is generated, and they have also industrial plants and hospitals and normal housing. And this is a relatively complex game. It's not the games that you see on your PCs, but it is a hypothetical scenario. But with this scenario, we were able to show that the model that's based on local computation of vulnerability, local computation of recovery, and system operation, where this emergency dispatch is repeated at every one of these time slices, that we can actually compute the behavior of the system. And we can see that there is this area here where the demand is not satisfied. The demand exists, the supply has dropped quite a bit, and the generation has recovered, but the substations for distribution have not. And so 10 days go by, 11 days go by, and only then does the supply meet the demand. And yes, they rise together because there is more repairs to the housing, and eventually after some time there will be a complete recovery. But in our simulation we let this time run so far, and we deliberately chose somewhat aggressive recovery functions so that we can see this. But overall it looks like the model is working. And then we were very lucky, well, these guys were not lucky, but we were lucky that there was an earthquake in Nepal, and also there is an equivalent project in Switzerland, equivalent to the RAPID projects that people go and take a look at what happened during the earthquake. So we got one of those, and we focused on the electrical power systems and water system and communication system. And then we went to Nepal. In fact, I went there only once, but a couple of master students and one of my doctoral students did so a few times, and they were able to get data as much as possible about the behavior of the system before, right after the earthquake, and during the recovery process. Unfortunately, the Nepali system looks like this, and it is really not a beautifully designed system, and it's a messy one. the other side of it is that they're not so concerned about state secrets or data protection, so we were able to obtain the data. But nevertheless, it is an exercise in patience, and it's also an exercise in understanding how things are different in the developed part of the world. So this graph is the amount of power that they're not having. These are normal, everyday power deficits in 4 different years, and you can see when it's cold in Nepal, they have a tremendous power deficit. And when it's even warm here, they still have power deficit. So the normal state of the Nepalese electrical power system is that there is no power for several hours a day. There are brownouts. So that also has to be kept in mind. So we did obtain the structure of the system. We know where the generation stations are, where the parcels are, where the distribution stations are. There is data on how much power drop in generation they had. They had damage in some 18 plants. Some 3 of them were repaired fairly quickly. But the other ones that are privately owned, some of them are still not repaired. And the reason for that is twofold. One is that they're difficult to access, and it's not so easy to do it anyway under the best circumstances. But the second one is that almost immediately after the earthquake, they had a new constitution, which India didn't like very much. So India put in some sanctions on Nepal, and until basically about a month ago, no trucks were crossing from India to Nepal. So no spare parts or anything else could be brought up to fix this. So that means that their recovery functions are going to look very, very different from they would here. And so the data that we obtained is not perfect. There are some areas of this data where we simply have no readings because the people didn't record anything for a day or 2 or 3. They were busy digging themselves out or helping their family. But one can see a couple of things. The red and the green lines are the supply and demand, and the demand is larger than the supply. There is a continuous deficit. Their technical generation capacity is there, but their losses in the system are very high also. And then there was the earthquake, and there are instantaneous drops in both the demand and the supply that the system can generate. And the demand kind of sort of recovered smartly. The generation was recovering more slowly because it was more difficult to do so. Then there was the aftershock on the 12th of May. We can see that too. And then the continuous steady state now for more than 300 days of permanent, basically, lack of power in Nepal, and 16-hour or 8-hour periods in a day when certain parts of the city in Kathmandu have no power whatsoever. So this is what the data looks like, and we can discuss whether there is some correlation here or how this evolves. But we see that the original graph of resilience of a system is actually reproducible from the observed data. And not only that, but we see that with our simulation we can get closer. We definitely are not missing by a lot the drop in service of the system by doing a simulation of this earthquake, trying to reproduce the distribution of the intensities in Nepal, looking at the state of the supply or the state of the electrical power system. And we can also, in some sense, reproduce the way that the demand and the capacity evolves. But what we are doing is we are using Western-style recovery functions, and theoretically we are all hunky-dory after 10 days. Whereas in the reality, the recovery lasts for a very, very long time. And so there is a significant discrepancy between our demand simulations, and there is less discrepancy between our capacity simulations. But in some sense, even though I was hoping that this will be the proof in the pudding, I cannot say that we validated our model, but it's not that bad. And in that sense, there is, I think, a good reason to continue working with this model and to try to refine it rather than to scrap it and start with something completely new. Definitely there is a lack of more precise vulnerability, and definitely recovery functions. We do not know much about that. Our model of the functioning of the Nepalese network is probably not how that thing functions in reality, but probably the biggest drawback is that we made assumptions about the correlation that exists between different pieces of infrastructure, and we tried to simplify things quite a bit, and therefore we omitted some of the correlations in the system. So anyways, back to this idea that we are going to model the resilience using this difference between the supply and demand. And what I would like to do now is to show you how this integral actually was computed in these simulations and what we did to get a relatively reasonable measure of the lack of resilience. So at the level of one node in the system, the way that we treated this is by looking at the difference between demand and the available supply. This available supply includes losses in transmission and losses due to the poor performance of the network. And we look at it from the beginning, when the event happened, until the time that we decide to stop observing the system. The geographic boundary is also included there. There needed to be a circle around Kathmandu beyond which we did not go, and we made that judging by the extent of the network. And we are using the singularity function so that we are not integrating here when the demand is satisfied. We are only integrating here in this region when there is not enough supply. So this kind of definition is fine, and we can also normalize it. The reason why it's important to normalize this quantity is because this integral comes out in units of megawatt hours, which is nice because people compute that in terms of power. But if this is a water system, it would come out in liter hours. If this is a phone system, it would come out in number of calls made hours. If this is some kind of a monetary description of the functioning of the system, it would come out in Nepalese rupee hours, or in dollar hours, or in Swiss franc hours. And there is the power of money, but we do not know what to do with this unit. A dollar-hour unit or a dollar-year unit is an unknown quantity. It is not relatable to anything that we know how to work with. We know how to work with dollars separately from time, but together it's a difficult quantity to understand. And so, among many ways to normalize, we decided to normalize with the demand. Because the demand is somewhat easier to compute than the supply. In our simulation, we assume that the houses are uncorrelated to each other, therefore simple addition will work. And once normalized, we can get into the 1-0 space and then obtain a non-dimensional quantity for the measure of resilience and try to work with it, because then we can compare different nodes. We can compare even different infrastructure systems in terms of their behavior. But to move from the node level to the system level, there was one big obstacle. We defined the lack of resilience in terms of the available power, available supply. But the available supply is a complicated quantity that depends on the operation of the system. It depends on what is the maximum capacity available, and then we have to take out all the losses that are occurring in the system. It also depends on the demand state, and over time the demand may be higher or lower, and the dispatch may vary. Therefore, some parts of the network that had plenty of power may tomorrow not have enough. And this quantity was a difficult one to deal with. And the most depressing part is that it is not an additive one. If you take a look at the system level, the available supply at each node, summed up together, does not give you a system-wide available supply because of the many correlations that exist in this. The correlations come from the operations model of the system. And on the demand side, we assume that the houses are independent of each other, and that if there is power in one house, that guy is going to use it regardless of there is no power in the other house, and nobody is there. So there we said, okay, we can do this kind of a summation. And so this is where we cheated a little bit on the correlations, and if we go a little bit more granular, we can see that there will be correlations among the behavior of different apartments in the same house, for example. And this comes back down to, for example, the ATC 58 kind of sort of calculation of business interruption or losses in a building where the correlation between different floors exists, and the same would then occur for the correlation in power demand on different floors. So we simplified a little bit here. And so bottom line is that the lack of resilience at the system level cannot be computed just by simply summing the lack of resilience at every node. There needs to be a more complicated sum that takes into account these correlations and network operations. And so to be able to move on in these simulations, what we did is we defined the quantity of consumption, which is basically what does a distribution node take. Is it the demand or is it the available supply? And whatever this node has, it is going to give out. So if the demand is smaller than the available supply, the consumption will be the demand. If the available supply is less than the demand, they will consume as much as they can, and that will be the consumption of the node. And this, we said, is uncorrelated, one node to the other, and therefore we were able to sum it up across the network and obtain this kind of sort of curve that bounds the graph from the bottom as the consumption, and based on that we can compute the resilience of one node, which happens to be exactly the same as the old formula for the resilience of the node. And then we can also move to the system level, summing up what the nodes are doing and basically making a difference on the system level of the available demand, of the generated demand, of the present demand, and the possible consumption in the system. And here again we can obtain similar looking graphs where we see that the consumption cannot be met. The desire to consume electricity is not there because we simply do not have enough supply. And we can, in the same way, normalize this quantity on the system level by looking at the system level demand and obtain a normalized measure of this area of the graph that represents somehow the behavior of the system. And this is all fine and nice, and to make all these Monte Carlo simulations run, my students made a bunch of software and they developed kind of sort of an algorithm where we first look at the supply nodes, supply the node level, we look at the system level. Here is the network functioning model, some kind of electric power dispatch. Then we look at the distribution nodes, we compare the demand to the available power at each node, including the losses in transmission and the losses due to the inefficiencies of the system, and then compute the consumption, and on the basis of this we figure out if there is lack of resilience or not. And this is repeated over time during one event and then generated for many events to conduct Monte Carlo type simulations. And the results are not exactly matching the Nepalese data, but are making sense. And then therefore we continue to use this thing. And what we find very interesting is that this formulation is quite capable of representing pathological cases. And this is not so pathological. In Nepal there was an aftershock, and in this kind of a formulation we can see that after an aftershock there will be another period where the supply is going to lack and lag the demand. And the integral that I showed you between T1 and T0 and T1 can actually compute this kind of can compute this the sum of these two areas and declare that as the total loss of resilience of the system. Then there are more pathological scenarios. This is the Pompeii scenario, where we have a very severe drop in supply and a somewhat more gradual, although that's questionable, drop in demand before people actually leave the place, and then we have nothing. It's just abandoned. And this way, in the framework that we have, we can compute some finite measure of lack of resilience, whereas in the functional framework, where one just takes a look at the area under the curve, the loss of resilience would be just infinite here. There is another interesting scenario, and that is the one of Port of Kobe. What happened there is that in 1995 they had a pretty big earthquake and the port was significantly damaged, and then they took several years to repair the port. In the meantime, the Japanese auto industry continued to function, and all of the transports of the cars from the Kobe area were moved to Osaka. And then they had a very beautiful port that could supply even the previous level of loading, but they had no demand because there were no ships coming to it. the situation has changed, hopefully. I don't know exactly what is today, but this is Stephanie Chang's data from about 2010 or so. Earlier, anyway. So this is a situation that they have there, and the functionality framework does not show this as an option. It doesn't, the framework is somewhat limited and cannot show this situation. And then there is this thing. This is a cellular network example. And the cellular network is a good one, and therefore during the earthquake it doesn't get damaged at all. But what happens is that everybody's mother wants to call you. And there is a huge amount of calls that is generated, call demand. And this cannot be met with the current state of the network. There is some reserve, but it is a normal reserve, not the emergency reserve, and therefore there is a lack of resilience. And it may affect us because not all of us, but maybe one of us will need to call 911 and would not be able to do so. And so this is an interesting graph that the functional framework will just not see at all, and we can see that there will be a lack of resilience. Even though there is no damage, there is no change in supply, there is only an increase in demand for reasons other than structural failures. So it is a nice thing to know that this can be done. Another thing that I didn't talk about at all, and it probably requires another whole talk, is the probabilistic formulation of lack of resilience, because all of this is done by Monte Carlo simulations, and if we could be given, if we adopt certain functional forms for the vulnerability and recovery functions, if the network model is relatively simple, we could integrate it in closed form too, and obtain at every point in time the distribution of supply, the distribution of demand. We could look at the reliability issue and statements that we want to have certain confidence that the lack of supply is going to be smaller than this, and that the time of recovery is going to be faster than that. So a probabilistic formulation is something that follows fairly naturally from this system. Another thing that we can do is not measure the integral, not produce integral measures of resilience, but look at instantaneous measures. So at a certain point in time, try to quantify how much is it that the system is underperforming. And measures like this are not so terribly difficult to compute, and they could have nice social or useful interpretations. So the one that is here is the percentage of the population in this region that have no power in 1, 2, 3, 4, 10 days after the quake. And so here we get 35% for a fairly large earthquake. Is it right or not? I don't know. But the question is that somebody from the city of Berkeley, somebody who does public policy for this region, can say no more than 30. Let's see what we need to do so that we don't go above it. And what is the probability that we will go about some threshold? We also see that the supply, that the system recovers very quickly, and using Western style recovery functions, we're basically done with the event 10 days later. Here is another one where the number of people, percentage of people without power is correlated to the magnitude of the earthquake. And here we can also put a threshold, say 15% is what we can take, and then for these larger earthquakes, for the earthquake magnitude, we can fairly easily translate into the requirement for base shear, basically the strength of buildings, and then come up with design objectives such that a certain percentage of people without power 24 hours after the earthquake is not exceeded, given that there is a certain magnitude of with a certain probability that's associated with the magnitude of the earthquake. So we can formulate a standard performance-based design assignment based on this. And so the model that is comprised of these vulnerability of recovery functions for both the supply side and the demand side, and contains a system operation model that takes care of the production, delivery, and fulfillment of demand in both normal and emergency situations, is something that this framework is something that we developed, and we applied it for the electrical power system. And there is a couple of guys who did this for a fictitious water system. Now one student is doing this for the actual Kathmandu water system. And we had a couple of people look at the fictitious communication system, and one of the students, Salome, is now looking at the cellular network in Kathmandu. So we will see how close or far they will get. But this framework is something that I wanted to present, and I think it's relatively good, and it would be great if more of us could try something like this so that we can see whether it operates on different systems and what could be improved in it. And certainly it is complicated, and it requires this system functionality description that we don't need for single object, for single elements of the inventory. But because now the electrical power system is working together as one big machine, we need this kind of a functionality model, operations model. We didn't take a look at many of the interactions, we only took a look at a few, but certainly there is a lot of interactions and correlations. But nevertheless, the model is relatively transparent. One can see what is going on. It scales up and down relatively easily. Most important, it disaggregates. We are able to find out the cause of the largest loss of resilience, the most important cause of the loss of resilience, or the second most important one, and therefore prioritize our work. And so when it comes to engineering community resilience, we have to do, my suggestion is that we continue using this model and to engineer at the level of the system of systems, to look at the community all the time and to descend to single elements of the inventory, houses or substations, only at the very last step of the design process, that we have to start the design process at the level of a community. And what are then the goals that we should fulfill? We should provide the means to reduce the vulnerability before the event. We should provide the means for rapid recovery. And we should try to promote risk reduction. And all these things are associated with money. And this comes from Swiss Re, who are the reinsurance company, and they'll look at the amount of potential exposure of a community and say, how could money that the community has, how could it be spent most efficiently to reduce the vulnerability? And some part of that fund money could be used for cost-effective engineering risk reduction, basically retrofitting or building better new buildings. Some of the loss could be bearable, and by public policy means it could be reduced significantly. And some of the loss may not be able. We may need to generate additional investment to be able to go through the recovery process. I mean, during the recovery process, we are spending a lot of resources, therefore we need money. And this, the insurance industry suggests that this can be covered by financial tools, such as earthquake insurance, such as catastrophe bonds, or other financial tools. And so the role of the way that I see it, if we engineer at this system of systems level, there is very good incentives for the structural and the financial engineers to collaborate. Because, okay, the public policy people, we need to talk with them, but possibly after we discuss with the financial engineers what is the optimal mix of financial and structural measures. How much of the current wealth that I have should I put in retrofitting? How much should I invest in a financial tool, for example, buy earthquake insurance? This has to do with the time horizon of ownership. It has to do with some kind of a fair price of a retrofit, and the use of value at risk models and expected shortfall models is something that we are still looking at to see how to optimize this. And one of the outcomes of this simple model is a curve that shows a cost effectiveness of improvement in robustness. So basically we just modified the fragility curves assuming some improvement in robustness, and there is an area of a positive return on investment, and an area where you can over-invest in robustness and simply never recover the investment because there is not enough risk in your area, in your situation. So to me, this link to the financial resource systems is very important, and I think something that we are going to work on very hard. But still, there are challenges in this model, and in modeling, there is one significant challenge. We need to look at the system operation and the component characterization. But much more important, I think, in terms of fundamental knowledge, we need to continue to quantify resilience better. But there is a lot of uncertainty in the system, and we need to devote a lot of our energy to quantifying the uncertainties. We should not be approaching financial people and public policy people with deterministic statements. We have to have a very, very good idea about the uncertainty structure of the problem. From the structural standpoint, probably a good thing to do is to compute a fair price of an effective increase in robustness. From the financial standpoint, they need to try to develop other new tools for financial risk transfer, not only insurance, not only catastrophe bonds. There is probably other things that could be done that could be better suited for one community than the other, and this portfolio of tools also needs to be developed so that we can optimize the diversification and the redundancy of our system. Again, on the fundamental knowledge level, we need to find out what are the parameters that we are dealing with so that we can affect some design loops, and we can start to think about how to design and engineer a resilient community. So there is quite a bit of work ahead, and not only in structures and finance, but also in preparedness, education, urban planning, public policy issues. But the one thing that I would like to conclude with is a statement that as the risk is growing in our communities, and as today here, and especially in the Bay Area, we see investments from venture capitalists in all kinds of startups. What I would like to say is that as our risk is growing, and therefore the investment in risk governance should be at least equal to the intensity of the investment in innovation. If we are innovating without managing our risk, this innovation is at an even higher and growing risk, and so somehow we have to alert the people who invest in startups that they also have to do this. They have to do risk governance and engineering resilient communities, one way or the other, maybe using this model, maybe using something else, it doesn't really matter, should be one of the top priorities that goes hand in hand with all the other phenomenal stuff that the techie guys here are doing. So before we go to questions, here are the people. Max, Didier, and Lee Soon are the doctoral students, and and Benedict are the master students who did the work in Nepal. So Max and Lee are developing this model and are doing the simulations. And the postdoctoral researchers are Simone Esposito. She worked with Junior Ervolino in Naples. Panos was Jack's student here. He worked on the LA project. And Marco Brocardo was Armin's student, and he worked on the stochastic ground motions here. And so that's it. So thank you very much for your attention, and let's take some questions.
Thanks, Božidar. We probably have time only for one short question. I'm not sure if we have a class right after this.
Probably, yeah.
So, any pressing question? Yes.
Božidar, is there a general appreciation of how to allocate the short supply after a crisis like this? And are there plans, for example, in the Bay Area? We're pretending there's not enough electricity, and somebody has to make a decision about who to allocate it to.
I agree, and I do not know how the allocation is. I know that for Switzerland there is no emergency dispatch planned.
I wasn't thinking about generation, I'm thinking about
allocation, dispatch.
No. Well, let me just say, suppose you have 100 substations and 30 of them are daily. Which ones do you fix first?
Oh, prioritization. This is a difficult one. I don't know what PGA probably has some kind of a prioritization list, but the question is that prioritization list based on the maximized profit or the maximized service? And those are different things. Service would be oriented towards hospitals and houses, and profit would be oriented towards Google and Apple. Somebody needs to ask this question. And I do not know what their plan is. But this is if I was them, I would maximize delivery to Apple and Google.
You're
recover so faster than your demand curve. I'll give you an example of a situation where that's reversed. I went to Yerevan in the 1990s, and I was there for a couple of months, and there was no electricity, there was no supply of water, and there was no heat, because the nuclear power plant had been shut down, and that supplied everything.
Yeah.
But the demand was the same.
The demand was the same.
Because Yerevan was unaffected by the earthquake.
Yeah.
But the plant, the power plant, which supplied everything, was shut down. And that went on for about 15 years.
Yeah. Yeah, this is
Before they recovered, before they restarted the plant.
clearly this is a case that we need to take. I believe that we can take it into account, but we can add it to the pathological case list. Yes.
If I can make a quick comment, it's great to see you still linking to our students, so that's a good thing.
Yes.
The other comment I have, you were normalizing the law to calculate the loss of resiliency with some demand, which to me, if you're going to use this as a tool for decision making, it's pretty much risk neutral. You are not addressing the risk attitude of the decision maker, which people do using a utility function.
Yes.
Instead of doing normalization, where you can choose the right function that reflects that risk attitude.
I completely agree. Yes. In what Panos is doing, we use a utility function to figure out the preference for earthquake insurance, and this optimization between retrofit and insurance goes directly to the utility function. So to do the demand, we should really multiply demand by the utility function here, and get a better estimate of the risk aversion. And then there is a question: is there more right after the earthquake or less? And here in the Bay Area, there is definitely a diminishing to zero function of this utility. So this is quite interesting. But what I'm trying to say is that here is a framework. This may not be the best one, but it's rich enough to identify all kinds of crazy things and to start thinking at the system level, not at a single building level.
Probably have one more quick question. Sort of following up on Bob's question or your comment on it, you said there needs to be more discussion between earthquake engineers and the financial sector, but not so much on public policy. But if I were selling insurance, I could say, well, you don't have to design for earthquakes and rolls, you just have to insure it, and then I maximize my funding.
Yeah.
But that may not be, it goes to whose money are you maximizing there? Public policy thing.
Yes, but I think that this is the second step. I think that we need to have a good structured financial model first to be able to rationally approach the public policy people and to exactly tell them this, that they need to step in and regulate this. They also need to be able to step in and say, do you deliver power to Google or to the hospital? This is a public policy question, but it cannot be all answered at the same time.
Well,
okay.
We have to end it here.
Thank you.
Božidar will be here a few more days. So
yeah, I'll be at the ERI meeting at San Francisco. So
please join me one more time.
Thank you.